All right, welcome to the fourth and final part of our introduction to the naming and representation of organic molecules. We've looked at straight chain alkanes, we've looked at cycloalkanes, we've looked at branched chain alkanes. Now, finally, a word or two on branched cycloalkanes, and then we'll wrap up. So, this first molecule on the screen here, the parent is cyclopentane, and you can see it has a substituent group of a methyl. So it seems entirely reasonable that this is called methyl. Cyclopentane. The parent is cyclopentane. The substituent group is methyl. We don't have to put a locant on that substituent group because it wouldn't matter which carbon the methyl was on. It would have the same molecule. You could just rotate it around, move it around in three-dimensional space, and get back to the same molecule. Okay, right now, for these next couple of examples, I've dropped the ball and stick models because it gets a bit hard actually to take sort of snapshots of them to include here, and I'm just going to use the skeletal model. Okay, so looking at this, we have a 6-member ring. So the parent here is cyclohexane. It's a substituent of methyl and methyl. And we call the first one where any of these happens the 1 carbon. I'm going to call that the 1. Now I could go 1, 2, 3, 4, 5, 6, and that would mean that these methyls would be on the 1 and 5 carbons, but I can get lower numbers if I go around this way. 1, 2, 3, 4, 5, 6. So I have the methyls on the 1 and 3 carbons. The idea is you want to, if you've got substituents off your parent, you want to give them the lowest numbers possible. So this is in fact 1, 3 dimethyl cyclohexane. Okay. By the way, if there had been 3 things hanging off, we call it tri, and if there were 4, we call it tetra. Okay, now what about this? Okay, well, the parent is again cyclohexane, 6-member ring. Okay, and we have 3 substituents. We have an ethyl, and a methyl. Okay, how are we going to name this? Well, we definitely want to put the 1 on a carbon which has some action. Okay, and if we put it here and go 1, 2, 3, 4, 5, 6, that'll give us the most action with the lowest number of carbons. So we have an ethyl on the 1 and 4 carbons. So we've got 1, 4 diethyl, that's 2 ethyls. And then there's a methyl on the 2 carbon, so 2 methyl cyclohexane. Okay, so again, technically that's one word, but you know, if you write like that because you're out of space, that's fine. Yep, and there we go. Okay. In general, when you're just dealing with alkanes, the cycles actually take priority to the straight chain. So if you had like cyclohexane, then you had like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hanging off it, then that would be decyl cyclohexane. Yeah, the cycle takes priority. Okay, all right. That's provided you're just dealing with a straight alkane. We'll see that That doesn't hold universally for other sorts of molecules. Okay, good. All right. So with that, that is as far as I want to go in these videos. So to recap, in thinking about naming, we've talked about the first 10 straight chain alkanes, we've talked about cycloalkanes, we've talked about branch chain alkanes, we've talked about branch cycloalkanes. And we saw 10 prefixes, which depended on the number of carbons. They're here on the right. So for example, for the straight chain alkanes, 1 carbon methane, 2 carbons ethane, etc., up to 10 carbons of decane. These prefixes you need to burn in your brain. We will use them again for naming of organic molecules of all sorts. And the good news is that they are recycled. They're used in different types of organic molecules. And we saw when we had branched alkanes, cycloalkanes, or just branch chain alkanes, that these prefixes were also used for the names of the substituent groups. Okay, and the rule in the naming which we basically had was, first of all, you find the longest chain, or in the case of branch cycloalkanes, the cycle. That's the parent. Okay, and then you find the name of the substituents, and you give them together with a locant, which gives you the position which carbon on the parent that's on, and you can put as many as these locants and substituents on as necessary. You didn't actually have to name the locant if it didn't make a difference or if it was obvious. Okay. Let me redraw actually one of my examples. This is actually methyl propane. When I drew the skeletal structure in video 2, I was a bit cavalier with that. I wrote it like this. I should have written it like I got it there. Yep. And so here's a long chain, 3. That gives you the propane, and here's the methyl. So the substituent is the methyl. We don't bother saying 2-methylpropane because there's no other place that methyl can go. Okay. All right, but that is the general rule. And we've also seen in the representations ball and stick models, which give us a lot of information. We saw the molecular formula, which just gives us a count of atoms. We've seen the structural representation, we've seen the condensed structural representation, and we've seen the skeletal formula. So actually, the example I just gave is this molecule. There's the ball and stick model for it. This is methyl propane. The molecular formula is C4H10, if you count all those up. The structural representation would be this. Hydrogen, hydrogen, hydrogen. The condensed structural representation would be this. CH3, CH, CH3, CH3. And the skeletal formula would be this. Yeah. Okay. That will give you a good starting point. So now in the rest of the material we'll be working through together, we'll be learning to name molecules like these on the cover of your workbook. And we'll be learning about the reactions shown here with these green arrows, which enable us to get from one sort of molecule to the other. I'm looking forward to it.